So again, welcome to Mathematical Structure for Computer Science. This is CS 113 class, also known as Discrete Mathematics. In these lectures, we're going to discuss the rules of inference. So our main objective is to go through what is a valid argument, also inference, the rules for propositional logic. In our previous lectures, we discussed about what is a propositional logic when we use the negate, disjoint, and also conjoint symbols. Also using the rules of inference to build arguments. Also the rules of inference for quantified statements, and also building arguments for quantified statements. So here we're going to revisit our Socrates example. I think we went through this example when we started with the propositional logic. So an example here said that, for example, if all men are mortal and also Socrates is a man, then Socrates is a mortal. Again, this is a logical statement. All men are mortal. Socrates is a man. So that means Socrates is a mortal. So how do we get the conclusion from the premises? And this is the concept we're going to learn in these lectures. Rules of, again, inference. So here we start with the argument. Here we say we can express the premises, which is above the line. So again, this is our premises here. This is again a propositional logic concept. And the conclusion that's below, that was our previous example again in predicate logic as an argument. So here we have the men and mortar. We start with all. So again, as we said, our upside down A with a variable means all items, whatever the variable represents. So here we are trying to say that all men implies to mortar, which means all men are mortal. And if all men are mortal and Socrates is a man, then Socrates also is a mortal. So again, this is how we write the predicate logic. We are using, again, from the example, we say all men. So we use the all X. Man is a mortal. And we say if all men are mortal and Socrates is a man, then also Socrates will be a mortal. So we'll see shortly that this is a valid argument using our, again, inferential rules. So valid argument here, we say that we will show how to construct a valid argument in two stages. First, for the propositional logic, and then for the predicate logic. Again, we covered these two topics already. What is a propositional logic and what is a predicate logic? And it's in our previous lectures, which also posted in the YouTube. So the rules of inference are the essential building blocks in the construction of a valid argument. So the two steps is we have a propositional logic using the inference rules and also predicate logic. Inference rules for propositional logic plus additional inference rules to handle the variables and quantifiers. So we know a propositional logic will be our basic variables concept using, example will be the conjunction, disjoint, and negate. Predicate is always a propositional logic with also quantifiers or variables also. So here we say an argument is in propositional logic is again a sequence of propositions. All but the final propositions are called the premises. The final, which will be the last statement, is the conclusion. So again, an argument in propositional logic is just a sequence of propositions, but always the final propositions, which are called the premises, will be the last statement. Also, the argument is valid if the premises imply to the conclusion. The last statement will be our conclusion. So an argument form is an argument that is valid no matter what proposition are substituted into its propositional variables. So if the premises are P1, P2 up to Pn, and the conclusion is Q, then we can say that P1 and P2 and P3 up to Pn implies to Q, always is true. So this is a tautology. Again, we discussed what is a tautology. A tautology means a statement, or in this case, our expression here, that is always true. So the inference rules are all arguments, simple argument forms that will be used to construct more complex argument forms. So let's start with here. So we can see here, we say P price to Q. And so that's our first, the premises, P price to Q, and not Q, therefore not P, which again is valid argument. If P is price to Q and it's not Q, then it cannot be P also. Because let's say 4 price to only 10. When you get 4, you get 10 to the right. But to the right is not 10. Okay, if to the right Q is not 10, then the left value 4 is not 4. Because always I know that when I get 4, I will get 10. So my condition of getting 10 is when I get 4. So if I say 4 price to 10, and now I didn't get no 10, then I didn't get no 4. So this is a corresponding tautology for this. We say not Q and P is price to Q. Then it's not P then. Because if P is price to Q means if we have P, then we get Q. But it's not Q. So if it's not Q, then it's not P. So this condition always is true. That's why tautology is again state expressions that again is always true. So this is example they gave to us here. If let P be, it is snowing, and let Q be, I will study the discrete months. So that's kind of my condition is P, and what I will do based on my condition is Q. So here we say that if it is snowing, then I will study discrete mathematics. So here I have my premises and my, again, conclusion. So I will not study discrete mathematics only if it's not what? It's not snowing. Because we say P price to Q. If P price to Q and P is, it is snowing, then Q said I will study the discrete mathematics. So it will be if it is snowing, then I will study the discrete mathematics. I will not study discrete mathematics, therefore that means it's not snowing. So this example we have here, P price to Q. If it's not Q, therefore then it's not P. Because the condition here said that if it's no, I will study discrete mathematics. So I'm not studying discrete mathematics now. The reason why, because it's not snowing. So this is a whole concept of, again, and the rules of inference. And also another example here is, okay, if P price to Q and Q also price to R, so we can see PQ, P price to Q, but Q also price to R. Then we can say P also price to R. Because since P price to Q and Q go to R, then P also should go to R. So this is the corresponding tautology. We know that P price to Q and Q also price to R. So if that's the case, then P also will be applied price to R. So a very good one will be our sentences example here. We say let P be it snow, Q be I will study discrete mathematics, and R I will get an A. So this means if it snows, then I will study discrete mathematics. If I study discrete mathematics, I will get an A. So this means if it's no, I should get A then. Because we say if it's no, then I will study discrete mathematics. If it's no, I will study discrete mathematics. If I study discrete mathematics, I will get an A. So therefore, if it's no's, I should get A then, because I will study discrete mathematics. And when I study discrete mathematics, I will get A. So this is again disjunctive. So we say P or Q. So if it's P or Q and it's not P, then therefore it can be Q. Remember, it can be P or Q. This is not implied. This is either P or Q. So if it's not P, then maybe it can be Q. It has to be Q, because we know all means at least one condition has to be true. So if P is false, Q must be true in order for this condition to hold as true. So that's why we say P or Q. It's not P, therefore it must be Q. If it's not Q, then P or Q will be false. Because you get false, false is false. So if you get false, at least the next one should be true. And this is the corresponding tautology. So we know that it's not P and also P or Q. So if it's not P and P or Q, it will imply to Q. Why? Because if it's not P, then it's Q. So we get Q and Q, because P or Q, one of them have to then, that implies to Q. So a very good example here. Here we say let P be the, I will study discrete mathematics, and Q be, I will study English literature. So here we can say I will study discrete mathematics, or I will study English literature, and I will not study a discrete mathematics. So if I will not study a discrete mathematics, then I have to study English literature, because it's all. I will study discrete mathematics or English literature. I'm not studying discrete mathematics, so then I'm studying English literature. So this is again the addition. Addition we say is P, therefore it can be P or Q. So P always applies to P or Q. So example will be let P, I will study discrete mathematics. Let Q, I will visit Las Vegas. So I will study discrete mathematics. So if I will study discrete mathematics, then I will study discrete mathematics or I will visit Las Vegas. Because we said P, therefore P or Q. Or we can say P or Q, therefore P or Q, therefore P. Or P applies to P or Q. So if P is I will study discrete mathematics, and Q, I will study Las Vegas. Oh, sorry, I will visit Las Vegas. So I will study discrete mathematics, or I will visit Las Vegas. And if I will study discrete mathematics, then I will study discrete mathematics, or I will visit Las Vegas, one of them. So next we go to the simplification. This time we are using again the and. So P and Q, therefore we have Q. If I have P and Q and then we have Q, with this and means for this expression to be true, both P and Q must be true. So that's why the corresponding tautology said P and Q will imply to P. So let's say P is I will study discrete mathematics, Q is I will study English literature. So if I will study discrete mathematics and also I will study English literature, therefore then I have to study discrete. This means if I do P, I will also do Q. So if I'm studying English literature, I will also study discrete mathematics. So our condition is if you are doing one of them, then you have to do the other one also. So we say that I will study discrete mathematics and English literature. Therefore, I will study discrete math. So this is the conjunction. We have P and Q. Therefore, we can say P and Q. So P and Q will price to P and Q. So which means if P is I will study discrete mathematics and Q is I will study English literature, then I can have a condition that I will study discrete mathematics, I will study English literature. So if that is the case, then I have to do both. Therefore, I will study discrete math and I will study English literature. This is for conjunction, which is and. So we also have the resolution. Again, these are all the rules: conjunction, disjunction, simplification, resolution. These are the rules of inference. So resolution said if not P or R and P or Q, and you can see the trick here, whether it's P, which is, sorry, P or Q, and not P or R, therefore it will be Q or R. So resolution plays an important role in AI, and it's used a lot in Prolog language. Prolog language normally is used again, right? AI applications, the rules. I'll say used to build a knowledge-based system, which is the Prolog. And also it's very good for writing expert system applications where you have if-then rules. So this is the corresponding tautology. Not P or R and P or Q will price to Q and R. So example here, we say let P be, I will study discrete math. Let R be, I will study English language. Let Q be, I will study databases. So here we can say, I will not study discrete mathematics, or I will study English language. And I will study discrete mathematics, or I will study database. Therefore, I will study database, or I will study English literature. Because you have not P or R and P or Q, and that will price to, again, Q or R. They are put for both. So using the rules of inference to build a valid argument, here we say the valid argument is the sequence of statements. Each statement is either a premise or follows from previous statement by rules of inference. The last statement always called the conclusion. So a valid argument takes the following form. We can have S1, S2, again, any amount of propositional logic or any amount of predicate. But at the end, we have our conclusion. So S1 up to Sn will be our premises, then C will be our conclusion. So let's see an example 1. From the simple proposition, we can say P and P price to Q. Show that Q is a conclusion, which means here we're going to say P and P price to Q. We write down our P. Then next we say P price to Q using the simplification. Then if P price to Q, then at the end we can say Q. Here we are trying to say that P and then P price to Q will give me Q. This is example 2. we have a hypothesis here. So here we say with this hypothesis, it is not sunny this afternoon and it is colder than yesterday. We will go swimming only if it is sunny. If we do not go swimming, then we will take a canoe trip. If we take a canoe trip, then we will be home by sunset. Using the inference rules, we can construct a valid argument for the conclusion. So here we say choosing the propositional variables, we can use P. So P means it is sunny this afternoon. Q means it's colder than yesterday. R means we will go swimming. And S means we will take a canoe trip. So T means we will be home by sunset. So based on the hypothesis, we can say not P and Q, and we have R applies to P, not R applies to S, and S applies to T. Again, when you read the question, these are the conditions we get. So the conclusion here will be T. That's the last statement. So we construct a valid argument here. So we start with not P and Q, that's a premise, and not P, simplification using again 1. Then R implies to P premises, not R will be modulus tolerance using 2 and 3. And not R implies to S. And also we say S implies to T. And then we have our T. So handling quantified statement, we said a valid argument for quantified statements are a sequence of statements. And also each statement is either a premise or follows from previous statements by rules of inference, which include rules of inference for propositional logic or rules of inference for quantified statement. So the rules of inference for quantified statement are introduced in the next several slides we will go through. So we start with the universal instantiation. All x, p at x, therefore p at c. An example will be our domain consists of all dogs, and Fido is a dog. So all dogs are cuddly, therefore Fido also is cuddly, because here we say Fido is a dog. Now we have universal generalization, which is UG. P at C for an arbitrary C, therefore all x, P at x. And as instantiation, EI, we say exists x, P at x, therefore P at C for some element C. So example here is there's someone who got an A in the course. Let's call her A and say that he got an A. So using the rules of inference, let's look at this example here. They say using the rules of inference, construct a valid argument to show that John Smith has 2 legs. It's a consequence of premises. Every man has 2 legs, so John Smith is a man. So let M at S denote X is a man, and L at X has 2 legs. And let John Smith be a member of the domain. So all x, m at s implies to l at x premises. Then m at j implies to l at j will be our UI inverse. Then m at j premises, l at j is modus ponens using 2 and 3. So this is a second example using the rules of inference to construct a valid argument showing that the conclusion, someone who passed the first exam has not read the book. Again, someone who passed the first exam has not read the book. Follows from the premises. A student in this class has not read the book, and everyone in this class, again, this class passed the first exam. So our condition statement here said, a student is in this class has not read the book, but everyone in the class passed the first exam. So which means the student that didn't read the book also passed the first exam. So let's see at X, donate X in the class. B at X, donate X as you read the book. And P at S, donate S pass the first exam. So we can see that some X, not everybody, some X are in the class. So C at S means X is in the class. And B at S is S as read the book. So here we are saying that some of the students are in class and not reading the book. All the students are in the class and we have P at S. Therefore, some students P at S and not B at X. Because we have P at S and not B at X. And C at S, C at S. So we'll represent the P at S and not B at X to all E at X. So these are some of the rules of inference. Example, so we say instant of S, C at X and not B at S is a premise. C at A and not B at A is EI from 1. Then C at A, simplification form. All X, C at X implies to P at S is premise. Then C at A implies to P at A is UI. Then P at A is MP from 3 and 5. Then not B at A is a simplification form. P at A and not B at A using 6 and 7. Then some X, P at S and not B at X will give us EG from 8. So these are some of the rules of inference. So now we return back to the Socrates example. We say X is men, so all men are mortals. Socrates is a man, therefore Socrates also is a mortal. And here we have all men are mortals. That will be our premise. And Socrates is a man, so Socrates also is a mortal then. So that's our UI. Now using universal modus ponens combines universal instantiation and modus ponens into one rule. So all S P at S implies Q at S. So P at A is where A is a particular element in the domain. And if I have P at A, then we're going to have our conclusion as Q at A, because here we have X. P at S implies to Q at S. So whatever value I get for the argument for P, that will give me the Q. So this again will be the conclusion of our lectures. Again, in these lectures, we learn the rules of inference, especially building a valid argument using the concept of, again, predicate, logic, propositional logic, constructing a valid argument. And again, wish you the best and thank you for your time.